In exercise 934, we're going to be looking at ozonolysis from the perspective of synthesis. So given a reactant, if we do ozonolysis with that, what will we get without having to draw each of the individual steps in the mechanism? So here they say predict the products that are expected when each of the following alkenes is treated with ozone, that's O3, followed by dimethyl sulfide, which accepts that third oxygen. The other two are going to be added to the molecule. So we're treating this first with ozone, and then in a separate step, DMS. Now, when you actually do this reaction, you have to be careful because that ozonide intermediate that we talked about in the previous video is explosive. And so you have to be careful that there's not a lot of friction around, not a lot of heat, because these intermediates you can get would explode. So when you're trying to draw the products for this, just hopscotching from the reactant to the product, what you want to do is to draw a sort of line through the double bonds. And you want to draw each of the pieces with those double bonds separately. Now you'll still draw the double bonds there, they just won't connect. So you could see how that is sort of the same molecule as the one above, just I've drawn where I had those breaks, where I had the double bonds connected, I've now separated them. So that's the first step in drawing the product. The second step is filling the double bonds in with the oxygens. Now these oxygens are coming from ozone, so you'll have these oxygens in the place of where the double bonds connected. Okay. The last step, this is technically your product. The last step is just to draw it in a way that looks less strange. This would almost never be drawn this way on a standardized test like an MCAT or a PCAT, so you want to be able to, or a DAT, so you want to be able to redraw this in the standard way. Now when you're redrawing stuff, I strongly encourage you to number the chain. Don't try to visualize it in your head or do some sort of mental acrobatics to rearrange this. Just number it. 1, 2, 3, 4, 5, 6, 7, 8. Now I'm not numbering this to name it, I'm just numbering it to keep track of stuff. So we have 8 carbons, we have 1, 2, 3, 4, 5, 6, 7, 8. I'm going to number those 2 just to keep track of everything. Okay. Well, on carbon number 2, I have a double bond to an oxygen. I have that ketone, as we discussed in that previous video. On carbon number 4, I have another double bond to an oxygen, so that's another ketone, because it has a carbon on both sides. On carbon number 7, I have another double bond to an oxygen. Because this has a carbon on both sides, that again is a ketone. So that's this one molecule on the left, and then the other molecule we'd have is this one. You'll notice that carbon, it doesn't have the fourth bond drawn explicitly. That means it's to a hydrogen, and so this has the double bond to the oxygen, but it has a hydrogen on one side. That makes it an aldehyde. And so you have 2 products here. You have this carbon chain with 3 ketones on it, and you have this one small aldehyde, and those would be the 2 products for this ozonolysis. So you're using ozone to break apart double bonds. This is the only reaction in this chapter where you're not just adding 2 things onto the double bond. You're breaking apart the double bond and replacing it with double bonds to oxygens. And you'll make either aldehydes or ketones. Notice one other thing that's really special about this reaction. In this reaction, you can break rings apart. You have a ring in the starting material. You don't have any rings in the products. So you're able to break rings apart with ozonolysis. It's a special feature. Okay, same thing. If we had this alkene and we treat it first with ozone, followed by dimethyl sulfide, the ozone adds 3 oxygens to each double bond. The dimethyl sulfide steals the third one, so you only have 2 per double bond. So start by drawing sort of break lines through all the double bonds, and then draw each of the pieces separately. So redraw the molecule, just don't, and even with the double bonds, just don't connect the double bonds. So you can see how that is really the same as the reagent. I've just separated the places that I had broken apart. Okay, and then where the double bonds connect, place the oxygens from ozone. So instead of those carbon double bonds connecting to each other, they bond to an oxygen. And so we'd really have two equivalents of this molecule here. We'd have two of these. So if you're just thinking in terms of species, you'd only have that one species of molecule. And notice that each of these are ketones. You have a carbon double bond to an oxygen with a carbon on both sides. So as we discussed, that is a ketone in the previous video. So those are your two products for this reaction. All right, next one. What if we have this molecule, we treat it first with ozone, O3, and then we follow that up with dimethyl sulfide, DMS. So the ozone is going to add 3 oxygens, the DMS steals the third one, so we're going to end up with just 2 oxygens that we're adding onto the carbon chain. Well, the first step is to draw a line sort of through that double bond. Redraw the molecule, but with the pieces separate where the double bond was. So you'd sort of have those two pieces. And you can see how that's really the same as the original molecule. I've just separated where that break was. And then insert oxygens where those double bonds connected. And so those are our products. Now technically those are the same molecule. They're just this here. Notice the fourth bond isn't drawn. That means it's to an implied hydrogen. So those are the same thing. We just have two equivalents of this molecule. And you'll notice that this is an aldehyde. We have a carbon double bonded to an oxygen with a hydrogen on one side. Immediately bonded to the carbon that's double bonded to the oxygen. So that's an aldehyde. Okay, next we have this cyclopentene. What if we bubbled some light blue pungent ozone gas through that and created an explosive intermediate and then stabilized that by adding dimethyl sulfide? Well, in that case, we'd be doing ozonolysis. You would draw sort of a break line through the double bond, redraw the molecule as it is exactly, even with the double bonds, just don't have the double bonds connect to each other. And where the double bonds used to connect, insert oxygens. Those are oxygens from the ozone. You'll notice ozone has 3 oxygens. We're only adding 2. The third one ends up going to dimethyl sulfide and turning it into dimethyl sulfoxide, DMSO, what you usually would think of as a polar aprotic solvent, as we discussed in that previous video. So this is the product technically, but it looks really weird. You want to draw it, points would be taken off if you don't draw it in the conventional way. So you'll want to redraw that in the conventional way. And the reason why I want that is because the answers will never be drawn like this on the standardized tests that you guys would need to pass. So I want you to be able to visualize this in the standard way, in addition to just drawing the product. To visualize that, I strongly encourage you to just number the carbon chain. Now you're not numbering it to name it, so you can number it however you want. It's just to keep track of stuff. This chain has 5 carbons, so we'd have 1, 2, 3, 4, 5. On carbon number 1, we have a double bond to an oxygen. And on carbon number 5, we have a double bond to an oxygen. So if we're numbering this, on carbon number 5, we'd have another double bond to an oxygen. Now notice there's a bond there that's not drawn in. That's to an implied hydrogen. And so here we have 2 aldehydes. Carbon double bond to an oxygen, and the carbon is also bonded to a hydrogen. That's an aldehyde. Carbon double bonded to an oxygen, and the carbon is also bonded to a hydrogen. That's an aldehyde. And we see that special thing happening again. We started with a ring, we end with a straight chain. You can do ozonolysis to break rings open. Here we have a bicyclic compound, so what would happen there if we treat this first with ozone, followed by dimethyl sulfide? So ozone will add 3 oxygens, dimethyl sulfide will steal 1 of them away, so we'll just have the 2 oxygens left, added onto the molecule. Well, first, draw a sort of break. Once you see ozone and DMS, you know this is ozonolysis, so you're going to break open the pi bond. draw a break through that double bond, and redraw the molecule, even with the double bond, just have the two pi bonds not connected to each other anymore. So that's that molecule, and we'll replace the bond to each other to bonds to the oxygens from ozone. Okay, well that is technically the correct answer, but you don't want to leave it like that for sure. You want to redraw this in the way that it would appear on a standardized test, like the PCAT or the MCAT. So I'm going to number this. It doesn't matter technically how you number this. You're just numbering it to keep track of stuff. So I'm going to go around this sort of part that is all connected, this ring that's left, 3, 4, 5. So this ring that's left is a 5-membered ring. So it's going to look like a pentagon. Now again, I'm going to number this. So there's our 5 rings. Now on carbon number 1, I'm going to have a carbon attached to that. And that carbon is going to be double bonded to an oxygen. Notice the other bond here isn't drawn. That means it's an implied hydrogen. And so this is an aldehyde. Carbon double bonded to oxygen. Carbon is also bonded to a hydrogen. On carbon number 4, I have the same thing. Another carbon coming off with a double bond to oxygen. Only 3 bonds are drawn explicitly to that carbon. There needs to be a 4th one. It's to an implied hydrogen. And so again, you have an aldehyde, a carbon double bonded to an oxygen. That carbon is also bonded to a hydrogen. And so we broke a ring open here because we started with a bicyclic compound that had 2 rings. After you break the ring open, you just have 1 ring left. And we were able to draw that in a more conventional way, just by doing some numbering. And we formed 2 aldehydes. For F, the last example here, what would happen if you treated this with ozone, O3, followed by dimethyl sulfide, DMS? Well, you'd recognize that as ozonolysis, you draw a sort of break in between the double bond. You draw each piece of this molecule separately. So you draw the same molecule, just have the double bond not connect one side to the other. And where they connected, insert oxygens. Those 2 oxygens are going to come from ozone. Ozone has 3 oxygens. The DMS is there to accept that 3rd oxygen and become DMSO. And so you end up, these 2 molecules are really the same. You end up with 2 molecules of this. And you can number them and see that those are the same. Right? You could see that this is 1, 2, 3, 4. This is 1, 2, 3, 4. So they're both 4 carbon chains with a double bond to an oxygen on the 2nd carbon. That's true for all of these. And so those are your products there. You'll notice that here you have a carbon double bonded to an oxygen, and that carbon is bonded to carbons on each side. So these are ketones that we have here. These ketones and aldehydes will come back not only in the next chapter, but in organic chemistry too. There will be a whole chapter devoted to them. So it's worthwhile being able to recognize them now. Remember that an aldehyde is a molecule that has a carbon double bonded to an oxygen, and that same carbon is single bonded to a hydrogen. And a ketone is a carbon double bonded to an oxygen. That carbon is bonded to 2 carbons on each side. It's a ketone. So when we do ozonolysis, we've seen the sort of procedure for predicting the products, and you always either make aldehydes or ketones when you do ozonolysis with an alkene.